Aloha. We're going to continue our journey through figuring out if things are particles or waves, or a little bit of both, those wavicles. But this is our first, or really the first foray into the branch of the electromagnetic spectrum that is X-rays. Those were first played with by a guy. His last name is pronounced Rentgen. I forget the year. But what he was messing around with was similar to the photoelectric effect. They were noticing all these different parts of the spectrum in certain characteristics. But those low pressure gas tubes, those are similar to what we played with the photoelectric effect. We take a glass tube and we rarefy it. We take a lot of the air out. Glass plates on either side in that glass tube, shoot stuff through it, see what comes out. And what he would then place around this are the equivalent of photographic film that would respond to a photon banging into it, and it would produce an image on a film. And you guys know that visible light photons you can block from that photographic film by just covering it with something that blocks light. Well, even when that film was covered with something that blocks light, it was still expressing the fact that it was getting hit by a photon. So this led him to believe there must be other photons out there, and they must have a lot of energy in them because they can travel right through the same items that block visible light. So that's what he was looking at. And it's these mysterious rays that went through a piece of black cardboard. So you could still expose photographic film even though you were trying to prevent the photographic film from being exposed. So the way he created these guys, very, very similar again to the photoelectric plate, this photoelectric effect. This then is a very strong battery. Remember, that's the positive terminal. That's the negative terminal. So what we're going to do is talk about electrons now. We're going to have electrons going this way. When they get to that end of the wire, that's a piece of metal there. These electrons now are going to go flying that way, very high energy. They're going to slam into this piece of metal. And if they slam into that piece of metal with enough energy, then it would cause this piece of metal to say aloha. And those alohas happen to be what we end up calling X-rays. And what he was trying to logicate his way through is to say, well, on a very small fundamental level, what's going on here? And there's electrons traveling towards a piece of metal that has a positive charge on it, but this is one of the croutons in the salad, if you will. Remember, when we talk about a salad, that's a joke phrase I use for the crystal lattice. All of the protons stuck into a very orderly fashion. As an electron approaches that, it's got some electromagnetic attraction, and as it goes, it could, if it's not quite fast enough, it could bounce off. If it's not going quite the right trajectory, it may end up doing something like this. This particular electron may end up doing something like that if it's going not quite the right speed to stick to this guy, or get bounced off by some of the electrons that surround it. So in either case, when this electron changes its direction, that's an acceleration. So charged particles are accelerating. When charged particles accelerate, they say aloha. That's where this stuff comes from. So when that electron slows down, it loses energy. When it loses energy, that energy is expressed as a photon. And we can figure out how much energy is in a photon, can't we? So when that electron loses energy, that energy appears as an X-ray. So if it loses energy, something had to do work. And what did the work was the salad itself, the crystal lattice, as that electron is approaching a proton. Remember, protons are positive. They have a higher amount of potential than electrons, so they're traveling through a change in voltage, a change in electric field. So that the Q is the electron itself. The delta V is as it's approaching the nucleus, stuck in the salad there. Remember, the way you calculate the energy in a photon is simply hf, Planck's constant, times its frequency. So that is, in general, how they figured out, okay, the amount of work is equal to the change in energy. Fine. The maximus amount of energy that could be lost by that electron is if the then electron does not get detected on the other side or after it bangs into something. So if this electron changes its direction, we can still detect it over there. If this electron changes its direction, we can detect it over there. And even if it bounces back, we can detect it after the collision. But what if we shoot an electron in there and then we don't detect it anymore? If we don't detect it anymore, then darn it, it had to get stuck in the salad, didn't it? So if it gets stuck in the salad, that's a good thing to keep track of, because that means its velocity went from whatever it had, down to 0. That means that's the maximus amount of energy it could possibly give off us. And if that's the maximum amount of energy it can give off, that's the amount of energy that is in that electron to become an X-ray. So now the Q of the electron traveling through that change in voltage there gives off an amount of energy that is maximum. And remember, frequencies are higher if you have more energy. Wavelengths are lower if you have more energy. And remember this formula: the speed of a wave is oftentimes communicated as the letter C if it's a if it's on the electromagnetic spectrum, it's just communicated as C, which is equal to the frequency times the wavelength. So wherever you see that letter F, you can replace it with C over lambda, and that's what you see over lambda right there. It's the letter F. And just remember, frequencies and wavelengths are inversely related. Their proportionality constant is the speed of light. So F over, again, as F gets bigger, the wavelength gets smaller. As the wavelength gets bigger, the frequency gets smaller. It's inverses. So if we want to know the minimum wavelength, shortest wave it could give off, HC over Q delta V. All we did is just have those two items trade places. And so what better to bring families together than physics, right? So these two dudes started playing around with these X-rays and trying to learn a little more about them. Back then, they were big in trying to figure out if things are waves or if they're particles or if they're a little bit of both, which I'm sure you guys all know. They're going to end up being a little bit of both. This, what I've drawn here, is what I jokingly again call a salad. This is the crystal lattice. These are the nuclei of atoms that are stuck in a very orderly arrangement inside a crystal. So what they'll do is they're going to shoot X-rays into this crystal. And, all right, let's shoot an X-ray, I don't know, right there-ish, boom, and let's have that X-ray bounce off. And I try to draw them at the same angle-ish. Remember the law of reflection, kiddies. Angle of incidence equals the angle of reflection. What I'm also going to do is say, well, gosh, the next opportunity for a collision happens a certain depth down. That depth is the next crouton in the salad, isn't it? The next nucleus. So if it's the next crouton down, that's 2 atomic radiuses away. That's just how deep the next item it could bang into, the next nucleus, is. So we're going to draw another one banging into that sucker. I'm trying to draw the blues parallel to the blacks. So when they bang on, they enter and leave. Now, boom. Huh? Okay. So now as they reflect off of this crystal, I have 2 different sets of waves if they are in fact waves at the same place at the same time. So if they do behave as waves, then there should be an interference pattern. When two waves are in the same place at the same time, they play with each other. They play with each other by constructively or destructively interfering. And you guys remember that if you have an interference pattern up here, then they must behave as waves. And sure enough, there was an interference pattern upon reflection. And so if there's an interference pattern, they specifically refer to as a diffraction pattern. And if there's one of those, then you can say, gosh, these suckers must be waves. They're saying aloha. The way we could tell how much farther this blue line traveled through the crystal, through the salad, than the black line, we will use this depth as a hypotenuse. So there's that. What I'll do is I'll extend this black and that black there, and holy shnikes, we have triangles. They should make an entire class dedicated to nothing but triangles. My gosh. Then what we're end up going to do is take a look at this angle here. That's what we'll call theta, that particular angle. And we know the depth of this guy. So what I will now highlight with this orange-ish color, boom, that line happens to be opposite the angle that we're playing with the green as a hypotenuse, right? And so this particular guy travels two of those orange line depths or distances farther inside the crystal. We're not going to pay attention to this. What we're going to do is we're going to start from where this guy would have bounced off. All right. So this, that, and that will be the additional path length that it travels. And remember, we talked about interference patterns going through those single and double slit diffractions. The additional path length is going to be a multiple of a wavelength if it's the first place they interfere. If it's the second place they interfere, it's two wavelengths, third place, whatever. So that particular path difference is 2 of those distances times the sine of the angle, 2d sine theta. And then the m lambda equals d sine theta is the formula we used when we first talked about diffraction. In this case, m lambda is 2d sine theta, and we had destructive interference at the half orders. Remember, sometimes constructive occurred at 1, 2, 3, and 4. Destructive was 0.5, 1.5, 2.5. That's what this pattern will follow also. Destructive is on the halves, constructive is on the wholes, and son of a gun, that means X-rays are, in fact, waves, which we kind of already knew. But then in our next segment about X-rays, we will see how they can also behave as particles. But that's it. We're getting there. We're very, very close to done. I'm sorry we're not hanging out in person first thing in the morning. I love the smell of physics in the morning, but I guess we'll have to get there, won't we? Yay, physics.